Hello everyone, myself Dr. G. Venkat Nagachandra, Assistant Professor at SR University, working in the Department of Civil Engineering. Today we will discuss about the primary sedimentation tank and activity sludge and trickling filters. So, in the previous lecture, means we discussed about the what is the purpose of wastewater treatment, and we discussed the screens, grid chambers, and equalization tank. In this lecture, we will discuss about the primary sedimentation tank and followed by ASP and trickling filters. Now means primary sedimentation tank. So it is located after the grid chamber. It removes lightweight organic suspended solids. Settling type will be the flow plane settling. Then so here means we need to provide a particular time that is called a detection time. Then only the suspended solids get settled bottom of the tank. So here detention time will be the major factor to remove the suspended solids. So see here from the primary sedimentation tank, the BOD removal is around 30 to 40 percentage, and suspended solids removal around 50 to 70 percentage. So this is the design criteria. The velocity should be around 1 centimeter per second, and detection time will be providing around 90 to 150 minutes. This detection time will be provided based on the concentration of suspended solids as well as the BOD concentration. The effective for particles, if it is greater than 0.1 mm, then this primary sedimentation tank will be effective. Then what are the tank features? Means here design purpose, it should be in a rectangular shape, maybe in circular tanks. So in a rectangular tanks, the flow along the length, and circular tanks, the flow will be radial flow. So what kind of effluent weights? Say rectangular, then another one circular. Rectangular here means outlet end. The circular will be the periphery. So where loading rate is means less than 185 meter cube per meter per day. So what are the factors affecting the efficiency? So one will be the eddy currents, wind turbulence, then thermal convection currents, density currents, and stratification. So these are the factors it influencing the efficiency. So this is the efficiency relationship. So R will be the removal efficiency equal to time divided by A plus B into time. Here A, B are the constants and T will be the detention time. R we already discussed, it is the removal efficiency. So design corrections is required for the field conditions. Then overflow rate, it should be multiplied with 0.65 to 0.085. Detection time also it needs to be multiplied with 1.25 to 1.50. It accounts for the non-ideal conditions. These are the design conditions for the primary sedimentation tank. So we will discuss about the one numerical problem about the primary sedimentation tank. See here, a primary sedimentation tank treats wastewater with the following data. What are the data? Flow rate is given. Initial detection time is given as 1.8 hours. Then these are the empirical constants. We discussed A, B values. Then surface overflow rate. Theoretically, it is given as 35 meter cube per meter square per day. So due to field conditions, the correction factors also given. The correction factors in previously we discussed, it is between this range to this range. So here fixed value is given for the detention time, it is around 1.4, and then overflow rate is around correction factor will be 0.75. So in this question, they ask you to calculate the theoretical removal efficiency, that is the R1, then corrected detection time. So detection time theoretical they provided, for a practical application it may vary. The factor also is given that actual removal efficiency, if the detection time will be varied, the removal efficiency also will be varied. How much? That also needs to be calculated. Then required surface area of tank also needs to be calculated before and after correction. So correction needs to be done here for overflow rate. Here also is given 0.75. What will be the before correction? What will be the after correction? And last one with the comment and how correction affect the design. Is it this correction will affect the design conditions or not? We need to check. These are the five problems we need to solve in this design problem. So as for our discussion, uh, the efficiency means theoretical removal efficiency, how to calculate R1 equal to T by A plus B into T. See here, so T is given as 1.8 hours, then A also is given zero point 0.4, then B also is given zero point 0.6, then time will be the 1.8. It is coming around 121.6 percentage. So since efficiency cannot be more than 100 percentage, so here efficiency we are considering as 100 percentage. So why we are means from 121 to 100 means the maximum is 100% only for practically, so we are limited to 100 percentage. Next step will be the we need to go for the detection time correction. So here the correction factor is given as 1.4 in the given question. So 1.8 is the theoretically detection time. Then for practical applications we are multiplying with the 1.4. Then it is coming is around 2.52 hours. So next step is the actual removal efficiency we need to calculate. So when we need to calculate after the correction of detection time. So time is a new time will be the 2.52 instead of 1.8 hours. So 2.52 divided by A, B parameters we know the same t value. So we got around 131.8 percentage. Here also the efficiency percentage will be more than 100 percentage. So we are considering upper limit as 100 percentage. So efficiency here also is getting around 100 percentage. Next one is the surface area calculations before correction. So area, how to calculate the area equal to what are the parameters existed based on the given data, how we need to calculate the area. So Q discharge divided by overflow rate. So here area equal to overflow rate will be done. So Q value will be 36,000 meter cube per day. So here also is given 35 meter cube per meter square per day. So based on these parameters, the area could be around 1028.6 meter square. This is the before correction surface area. So next we need to go for the area after correction. The corrector overflow rate will be the means theoretically it is around 35. The corrector factor will be 0.75 given in the question. Then corrector overflow rate will be 26.25 meter cube per day per meter square. So here area means modified area, correction after area will be 36,000 divided by 26.25. It is coming around 1371.4 meters square. So these are the means area is increased, then efficiency will be the same after correction. So the area increased from 1028 to 1371. Then detection time increased from 1.8 to 2.52 hours. Ensues so better settling under real conditions. So what we means discussed here in a primary sedimentation tank, we need to calculate the removal efficiency. So here removal efficiencies basically depend upon the detection time as well as the surface area. If we are means changing these two parameters, how the efficiency will be varied. Basically, this question will be understood that these parameters are very important to settling of suspended maybe to degrade of organic matter, that is BOD. So it's very important. So in the means in this problem we calculated these all the parameters what we discussed. So next process will be secondary treatment, that is activated sludge process. So activated sludge process is used during secondary treatment of wastewater. Activated sludge is a mixture of bacteria, fungi, protozoa and rotifiers and maintained in suspension by aeration and mixing. So basically means in aeration tank we need to means provide a kind of bacteria as well as the organic matter present. So that's why means it is kind of a mixture of bacteria, fungi, protozoa and rotifiers maintained in suspension by aeration and mixing, so that whatever food is coming in the influent, it can degrade by the microorganisms. So in this process, a biomass of aerobic organisms is grown in a large aerated basins. These organisms break down the waste and use it as their food to grow themselves. So activated sludge process returns sludge, settle sludge to the aeration basin in order to maintain the right amount of organisms to handle the incoming food. Activated sludge process have been removal efficiency in the range of 95.95 to 98 percentage than the trickling filters. See, in the primary clarifier, what will be the removal of BOD? It is around 30 to 35 percentage. So while means after next to primary clarifier, if we are means choosing the means right secondary treatment unit as ASP, then it should be removal of BODs around 95 to 80 98 percentage. But here in the two separate units is there. One is the aeration tank and followed by secondary clarifier. In the primary means after primary sediment is tank, there will be aeration tank. Here we need to provide the aeration so that what are the microorganisms present in the tank should be in a suspended state. Then what are the organic matter present in the water, it gets eaten by the microorganisms, and microorganisms population will be grown. And the next to the aeration tank there will be secondary clarifier. Here we need to provide some kind of residential time, so that means whatever the sludge it is there, it gets settled at the bottom of the tank. Then to maintain the microorganisms to organic matter, so some of the returned sludge we need to send back again to the aeration tank. So means it is the recycling ratio. Recycling means what are the means after treating sludge needs to be sent again to the main tank, so that ratio needs to be calculated. And also what will be the under means recycled biomass concentration, and what kind of means concentration is coming from the secondary clarifier we need to calculate. See next slide, working of a activated sludge process. So here, so we already discussed the primary clarifier, that is over. The removes the art means part of suspended solids, reduce the organic load on the ASP. So that's why primary clarifier is there before of ASP. So next after primary clarifier we explain aeration tank. It here contains influent and activated sludge. Activated sludge means here mixture liquid. It contains different kinds of pathogens. Maybe bacteria means in bacteria it's contain within bacteria, kind of sulfate reducing bacteria, This kind of different kinds of bacteria existed on the this sludge. So MLSS control here, maintain for effective treatment efficiency, we need to maintain the particular microbial growth. Then next one, the aeration supplies oxygen and keeps sludge in the suspension. So generally means we are taking sludge, it contains different bacteria. If it is settled at bottom, it won't take the organic matter present in the wastewater. So it should be always in the suspended state. So for that we are providing the aeration to the tank. So next one is the followed by secondary settle. Separates the treated water and sludge. Here if you are providing some kind of detection time, what will happen? The means sludge will be settled, then remaining treated water will be sent to the further treatment if it is required. Otherwise they will dispose on the water bodies. Then effluent, clear water discharged after treatment. For suppose municipal wastewater, it is not required tertiary treatment. If it is industrial wastewater, after secondary treatment also needs to go for the tertiary treatment, that is special treatment is required. Then return sludge. So here the portion of recycle sludge back to the aeration tank. Why we need to provide again the settled sludge to the aeration tank means, so it should be balanced between the organic matter as well as the MLSS concentration, that is the mixed liquid suspended solids, that is the bacteria growth. If it is not maintained, what will happen? The organic matter present in the wastewater will not be degraded, so effluent concentration of BOD will be higher. So to maintain this effluent concentration low, we need to maintain the MLSS concentration and organic matter should be in the balance. That is called as food to microorganisms ratio needs to be calculated. Then excess sludge. So what are the means? Some portion of sludge we are sending back to the aeration tank. Then remaining sludge we need to go for the further treatment before disposing on the environment. So here we need to go for the anaerobic digestion. Maybe aerobic digestion option also is there. After kind of this treatment for excessive sludge, what will happen? Then it is called as nutrient rich compost that we can use for another purposes. This is the basically working of activated sludge process. So main mechanism here is the, so to maintain bacteria in a suspended state. So water is coming in the reactor in a horizontal flow direction, so that it is in suspended state. Bacteria means organic matter is breakdown by the microorganisms. So what are the means BOD present in the water get reduced, it is eaten by the microorganisms. If they are taking this food, then it goes by the, so yield also will be increases, means growth of bacteria will be increases. So microorganism growth will be increases means BOD concentration also will be reduced. Why we need to send again to the settle salts to the aeration tank means here is to maintain the microorganism growth as well as the food concentration in a balanced way. Then only the BOD concentration will be reduced in the reactor. So this is the typical diagram of ASP. C is the influent. Q will be the influent flow. It is coming from the primary clarifier. Then S naught will be the BOD concentration, initial BOD concentration, that is called as food. Food here will be the BOD. X naught. X naught means here the microorganisms concentration, that is called as X naught. That influent is going to the aeration tank. This is the aeration tank. So here we are providing the some kind of mechanical aeration. Maybe we are providing aeration to the reactor, so that what will happen? The sludge won't be settled. It will be always in the means suspended state. So whatever the bacteria is there in the means whatever the organic matter present in the wastewater, it can be eaten by the microorganisms. Then next unit is followed by aeration will be the clarifier. Here we are providing some retention time. So here the sludge will be settled at the bottom of the tank. Some portion of sludge we are sending back to the aeration tank. Those concentrations here, QR will be the written flow rate. So XR will be the written or underwater biomass concentration. SR will be the underwater effluent BOD concentration. The sludge here, the amount of sludge wasted here means flow will be wasted flow will be QW. XR will be the under water biomass concentration. Here effluent will be Q minus QW. Here QW we are wasting, so remaining water will be then a circular. So here the effluent flow rate will be Q minus QW, and XC will be the effluent biomass concentration. SE will be the effluent BOD concentrations. The concentration, if you want to dispose on any water body, the concentration BOD concentration should be below 30 milligram per liter. So this is the one of the efficient process to remove the BOD. It is around 85 to 90 percentage. So these are the abbreviations I have explained in the previous slide, and units also is given. It is very important. Unit is C, volume in a meter cube. S naught, what is the S naught? Initial BOD concentration or substrate concentration. S will be the effluent. X naught will be the concentration of biomass. XR will be the concentration of biomass in the return line. XR will be the concentration of biomass sludge drain. Here XR and XR, these both are same only. The XC value will be the concentration of biomass in the effluent. So design considerations. So here for a design of activated sludge process, here is two equations already derived from it is the equations as taken from the Metcalfe and Eddy. So next class I will show the derived equations. See now equations used for design of aeration tank. Theta C will be volume multiplied with the biomass concentration in the aeration tank divided by QW into XR. QW, that is the wasted means water. The XR will be the underground microorganisms concentration. X will be the aeration tank biomass concentration. Here also one more equation, 1 by theta C equal to Q will be the flow rate, Y will be the yield, S naught will be the initial BOD concentration, S will be the effluent, and Vx Kd will be the decay constant. During the growth of microorganisms, so decay rate also will be there. So we need to consider decay rate also. Then next one is the mass balance around Clarifier. So the final equation here will be how to calculate the QR. QR equal to Q into X minus QW into XR divided by XR minus X. This is the way we need to calculate the recycle flow rate. Then recycle ratio will be QR divided by Q. So now we will solve one numerical problem, how to calculate the recycle ratio, how to calculate the wasted volume, how to calculate the kind of volume of the aeration tank. So you see, read the question properly. So an activated sludge process is to be used for secondary treatment of 15,000 meter cube per of municipal wastewater. So water is coming from the municipal wastewater. So after primary clarification, the BOD is 170 milligram per liter. So what is the initial BOD concentration? 170, and it is desired to have not more than 25 milligram per liter. it is a given target, the effluent concentration won't be more than 25, means that is as E equal to 25 milligram per liter is given. So a completely mixed reactor is to be used, and pilot plant analysis has established the following values. See here, hydraulic reduction time, that is theta c is given as 10 days, yield coefficient y equal to 0.5 kg per kg, then kd value, decay constant is given as 0.05 day inverse. So next will be the assuming an MLSS concentration of 4500 milligram per liter and an underflow concentration of 12,000, means here MLS concentration means X equal to 4500 milligram per liter is given. Underflow concentration means XR will be 12,000 milligram per liter from the secondary clarifier. Determine the volume of the reactor, the first question. The second one with the mass and volume of solids that must be wasted each day. So mass and volume means QW need to be calculated. Then recycle ratio also needs to be calculated. Recycle ratio means here QR by Q. These are the three questions we need to address. First, in the question is given as Q equal to 10,000 meter cube per day. Theta C also is given 10 days. So we know the formula 1 by theta C equal to, this is the equation. If we are substituting these equations, so S naught we know, S we know, Y also know, Q also know, KD also given, X also given, theta C also is given. Only unknown parameter will be the volume. So after substituting these all values, the final volume will be 1611 meter cube. That means, so volume of the aeration tank will be 1611 meter cube. So there will be another equation, theta c equal to V into x divided by QW into XR. Theta c we know, volume also we know, x also we know, XR also known. Only QW value needs to be calculated. Here QW XR equal to, so Vx divided by 10, that will give the 724.95 kg per day. So this is the mass is wasted. So along the mass we need to calculate the volume also. What will be the volume? If the concentration of XR will be 12,000 milligram per liter, QW you know, QW we need to calculate. QW equal to 724.95 divided by XR concentration will be 12,000 milligram per liter, that is 12 kg per meter cube. It is getting around 60.41 meter cube per day. So here we need to calculate the QR by Q. So we know the formula of QR, Qx minus Qw XR divided by XR minus X. Q we know, X value also know, Qw XR calculated, XR no, X also given. So as per this equation, the QR is getting around 8903.34 meter cube per day. This much of water is circulating out of 15,000 meter cube per day. So in that we need to calculate the recycle ratio. 8,903.34 divided by 15,000. That is the actual inflow rate. Then it is around 0.59. So as per the design conditions, the means recycle ratio should be around 0.6. So I will briefly means what we discussed in this lecture, especially ASP. Here means main mechanism involved in the active sludge process will be the microorganisms needs to be introduced in the aeration tank. That also should be in the suspended state. For that we are providing the aeration. Means here BOD will be the organic matter that will be there in the wastewater. So if we microorganism will be there in the suspended state, it will be eaten organic matter by microorganisms, so that in this process what will happen, BOD concentration will be reduced. Next will be the secondary clarifier. Here the sludge will be settled. The some portion of uh, sludge needs to be introduced into the aeration tank. Why we are doing again back to the means aeration tank will reason behind this. We need to maintain the ratio between microorganisms as well as the organic matter. Then only BOD removal will be happen. Particularly in this design problem, we discussed how to calculate the volume of aeration tank, and how to calculate the amount of mass wasted, that is QW into XR. Next will be the what will be the volume to be wasted, that is the QW, also calculated. And also last one with the needs to be calculated the recycle ratio. So that is QR by Q, that is also calculated, is getting around zero point 0.6. So these are the important parameters when someone is designing a ASP. These are the some of the design parameters needs to be considered. Then only efficiency will achieved around 85 to 90 percentage. In upcoming class, we will discuss about the remaining secondary treatment units. Thank you very much.